In the previous lecture, I discussed that the capacitance of a capacitor depends upon the shape of the capacitor. So if you change the shape of a capacitor, the capacitance also changes. Hence, we need to discuss the capacitance in the case of different geometries. Okay, first one is parallel plate capacitor. As the name itself suggests, the shape of the capacitor is parallel plates. So let us consider two parallel plates. And those plates are charged. One is charged with positive Q, another is charged with negative charges. So let it be again Q but negative charges. Total amount is negative Q, and in the first plate total positive Q charges are there. They are plate 1 and plate 2, P1 and P2. Okay, now in such a case, now if you connect a battery also, you can connect it to a battery, then only it will get charged. I am not showing that diagram here. If you want to charge those plates, you actually need to connect it to a battery. So in my diagram I am not showing the battery, but originally when you connect it to a battery, then only the plates will get charged. Okay, now let the separation between them is D. Between the plates, separation is D, and in between the plates there must be an insulator or dielectric. Here it is air. Okay, so in between air is present. Now if you want, I will connect it. This will be the original diagram. When you connect it to a battery, then only it will get positive and negative charges. This is the original diagram. Most of the cases, sometimes we will leave the battery and all other things just for our explanation purpose, but you must keep it in mind that it must be there always. Okay, now since there is a positive side and there is a negative side, there will be an electric field from positive to negative, isn't it? This will be the electric field E. And when two metallic plates are there, the electric field in between the plates, in between two metallic plates of charges, surface charge sigma, the electric field is E is equal to sigma by epsilon 0. We discussed in the first chapter using Gauss's theorem. So the electric field in this case is also sigma by epsilon 0 in between the plates, isn't it? Now you must know one more formula. You already know that E is equal to minus dV by dr, where V is the potential and R is the separation or distance. In this case, for capacitor, you can write it as V by D, because V is the potential. If you take it as V and if distance is D, then you can consider it as V by D. Negative sign simply is used for the direction of E related with V, so we can neglect that one here. So in general you can write E is equal to V by D, from which you can get V is equal to ED. You must know this relationship. So you can use this expression V is equal to E into D, where E is the electric field and D is the separation. Now you already got the value of E. In this case it is sigma by epsilon 0. So you can substitute sigma by epsilon 0 and the result E, isn't it? Now you have the relation Q is equal to CV, or C is equal to Q by V, isn't it? Now let us take this expression. What is Q? The plate is having a surface charge density sigma. Its area is A. So total charge Q is equal to surface charge multiplied by total area, we discussed in the first chapter. So Q is equal to sigma A divided by what is V? You got V is equal to sigma D by epsilon 0, isn't it? Sigma and sigma will cancel and epsilon 0 will move on to the numerator. So you will get C is equal to epsilon 0 A by D. This is the expression for capacitance of a parallel plate capacitor. And from this expression you can see that the capacitance of a parallel plate capacitor can be increased by, first one, you are having the expression C is equal to epsilon 0 A by D. So if you increase A, C will increase, isn't it? So first method is by increasing area of plates. If you increase A, then capacitance will increase because they are directly proportional. Second one, decreasing the separation, because you can see D is in the denominator. D is nothing but the separation between the plates. If you decrease D, C will increase, isn't it? That is the second method. Now third method, which we will discuss in the next lecture, that is by using a dielectric material of high dielectric constant between the plates. In this case, we consider that air is there in between the plates. Instead of air, if you fill some other dielectric material, then you can increase the capacitance of that parallel plate capacitor. So the effect of dielectric and how it will increase the capacitance will be discussed in the next lecture.